Hello YouTube, we're finally back with some more reviews, and today we're going to have a look at this ScanaPLUS 100 MHz logic analyzer from IKA Logic. In this review we'll be unboxing this little fella and test its performance with some fast switching FPGA generated signals, and finally we will also compare it with the cheaper and open source Open Bench Logic analyzer. But now let's first have a look at what's inside the box. The box itself is relatively small, so the unit itself must be small. It says that it comes with the device itself and a couple of probes and a USB cable. The ScanaPLUS contains 9 input channels, so there is 10 grippers inside the box, and the box is nicely crafted. Here is a side view of the unit itself, I guess, and another side view, and on the back we have some information about the ScanaPLUS. It's a 100 MHz logic analyzer, which means that the sample rate is 100 MHz at maximum. We'll be testing this out to see the performance and to see how and at which frequencies it can actually distinguish a signal, a logic signal. The great thing is that it has some adjustable logic levels and is protected. So the inputs on this can handle a lot of different voltages. And the great thing as well is that it not only have logic inputs on the channels, but some of the specific inputs also have a specific and special features such as RS-232 or Can Bus, which otherwise on other logic analyzers would require some external circuitry for converting the voltage into appropriate levels. And then of course it comes with some software which we are about to install later on in the video. But now let's open up the box and see what's inside. Alright, there we go. We have the unit itself. Yet again. Nicely sized and well packaged. Seems rocked and solid. Not too many unnecessary labelings, though it would have been nice to have the channel numberings out here. I guess that we can see that on the back of the box, where it says ground is at the top, then we have channel 9 and then channel 1 at the bottom, but that would have been nice to have on the front label as well. We have the USB input, say USB mini, on the left, and we have the channels on the right, and that's about it. Not that heavy, but still seems rigid. ScanaPLUS, IKA, made in France. Alright. So let's continue with the box where it says more. So apparently there we have to lift this up to get to the other accessories, which it says here, use this place to securely store your accessories. Alright, so here we have some accessories. We have a USB cable, alright, a USB mini cable, and then we have the different wires for the channels. And of course the probes. That's great. Let's open up this back probes. Oh, that can be difficult. Alright. And let's check the quality of these. Because the probes is always going to be an issue when getting around, because you can get these in very, very different quality. Some will just try to attach but will then eventually fall off. We've experienced that with a couple of cheap Chinese clones, logic analyzer clones, and the clamps that they come with are really cheap. So we'll be testing that, how good these clamps are and how good they are at gripping to our different terminals. But, I mean, testing wise right now, they feel right, and they feel quite solid as well. So I'm alright. They seem fairly alright right now, but let's see later on when we test it. And the great about these clamps though is that they come with attachable wires which can be plugged in either there or on the other side, which is this end of the cable plugs into the probes and the other end goes into the logic analyzer. So that's great. And of course this is color coded as well, where we have the black wire in one end or brown. Alright, so that's about it for the unboxing. It seems quite neat, and I'm looking forward to install the software and see how it will perform. So let's head over to the PC and see how it installs. Alright, so here at the PC I visited IKA Logic's homepage to download the software. So let's go to the downloads and manual sections. In this section we can see that we have the logic analyzer software, the Scanner Studio, and below the drivers it says that we don't actually have to install any drivers as they will be automatically installed when we plug in the device, so that's good. So let's go to the Scanner Studio page to download the software. Oh, that's great. Here in this page we see that both Windows, Linux and Mac OS X is supported. So we're not only limited to Windows and Linux, but Mac OS X is also supported. Below here we find some of the features of the ScanaPLUS Logic Analyzer software, the Scanner Studio. For example, we have the supported protocol decoders such as Uart, I2C, SPI, 1wire, Can, etc., which means that we can lock these signals and get them decoded into text or hexadecimals for easy recognizing. So let's download the software for Windows. Furthermore, I need to mention that you can also download other decoder libraries from their supported repository, where you can also upload new libraries yourself. For example, you can see that it actually supports the DHT humidity sensor, the DMX512 protocol, 4-bit LCD display, I2S, I2S, sorry, Manchester coding and MIA protocol for GPS receivers, for example, PVM, etc. Alright, let's go ahead with the installation and see how it goes. Now here at the installation, let's go ahead and install the Scanner Studio. And we are asked if we would like to install the FTDI drivers as well. So that's what they mean with that the drivers will be selected automatically. So yes, we will go ahead and do that. And wait for it to install. Alright. Couple of installation windows, and off we go. Okay, I think we're ready. Let's launch the Scanner Studio. New protocol decoders have been added or updated. Right, so this is a list of the supported decoders that has been installed. And there are some updates available, so let's download the updates and install them. Alright, so the decoders has been updated, and we can now choose our ScanaPLUS device. Ah, I see, a demo mode. So this is the graphical user interface, which is actually quite neat. It's similar to a lot of other logic analyzer softwares. We have the color-coded channels to the left, and you're able to name them, and in this case maybe even also select a voltage. And here at the demo window we could then take a look and analyze some of the data. We could of course add a time marker. We have analyze tools, we have a marker up here, so we can zoom in and figure out what is the width of this one, though it doesn't tell me when I hover, as with other logic analyzer softwares. But I can add a marker and it snaps onto the edges, which is great. So I can add one marker there, add another marker there, so we can see the times down here. And I could also select measure, I guess, and snap onto it to see that the time of this clock pulse is 579.34 microseconds. And I could continue to do that with the low time. So that is quite intuitive with this snap on, and it doesn't really bother me that I can't hover. But this is much better indeed. Okay, so that was measurements, but we can also add a decoder. Here in this demo example we have 4 data lines out here, and we have a clock pulse, it seems like. So we could probably analyze these signals as a parallel bus. So we go to the decoder and add a parallel bus decoder. Yes, makes sense. And we also have to select the channels, which is, in this case, these are not used. Then we have channel 4, 5, 6, and 7. LSB first. And our clock signal is at channel 3 at rising edge. So let's see how that works out. Alright, it's been analyzed. We have the parallel bus over here, and if we zoom in, we have some analyzed data. Hex 20, 0, looks good. We can see it on hover, and what about here? 80, D0, and so on. So with this analyzed data on the actual clock pulses, we can of course see individual traces and data signals, what they correspond to, but we also have an export function, which is great, that we can go to this Hex View and get a complete overview of the current analyzed data, which can be copied of course to used anywhere else. So now that we've gained a bit of experience with the Scana Studio, the software for the ScanaPLUS logic analyzer, let's go ahead and hook up the logic analyzer to a test circuitry. In this case, I'll be using the Basis 2 board, which is an FPGA board for generating a high-speed signal. So in this case, I've hooked this Basis 2 board up to this oscilloscope, where we'll be having a look at the signals as well. But now let's take the ScanaPLUS logic analyzer and hook it up. So now everything has been hooked up. We have connected the probes from the ScanaPLUS, and I must agree that I am happy with the quality of these probes. They also say made in USA, so that must be a sign of the proper quality. But these probes attaches very well to the connectors. I've connected them to the ScanaPLUS, and let's connect this to the PC and start up the Scana Studio software that we just installed earlier. Alright, so here in the Scana Studio, it says not connected, but if we press here, we'll get connected down here. So we should be ready to catch some data. Let's turn on the board here, where we will be able to see on the oscilloscope that a signal has been generated. Right now it's generating 50 megahertz signal, which is just right from the oscillator, but I can toggle this with the switches to pre-scale this signal so we can test different frequencies. Let's see what happens with the first one. It goes to 16.6 megahertz, the second one 10 megahertz, and both of them 7 megahertz, and so on. So with this we should be able to test the capability of the ScanaPLUS to see if it really works out with the 100 megahertz bandwidth as they write. So in the Scana Studio, let's go up and say configure. And here on the left we see that the sampling rate is set to 100 megahertz, and we can configure the inputs. Right now all of our inputs is just 3.3 volts, so that's alright, but if they weren't, we could select some different voltages here, which is why the ScanaPLUS is great, because it supports these different voltage levels. So if we go on, here is a configuration sheet of the special input options, as I mentioned earlier, the RS-232, LIN input, CAN bus, etc. That's also right, so we press finish. And now we should be able to make a measurement. We press start, waiting for trigger. Alright, so it's read something, but the first input signal is just high. Just being high. Well, for a 50 megahertz signal, a sampling rate of 100 megahertz is a bit of an issue, and that's also why the signal is read as high all the time. It could also be read as low. So let's try to reduce the frequency a bit. You'll see a 16.6 megahertz signal. It's a bit rounded. That's due to noise and capacitive. The capacitance in the outputs, which is not matched. The output impedance is not matched. Anyways, we should be able to recognize it as high and low levels anyways. So that's 16.7 megahertz. Let's try and do a measurement inside Scana Studio again. Alright, so now it seems like we got something here. Let's zoom in on that. Alright, okay. Well, doesn't really look square, a proper square. Well, that might be due to the sampling rate again, but still, I would say that 16.6 megahertz, that's about, well, about 1/8 of the 100 megahertz sampling rate, and this is not a sine wave, it's just logic square wave, so we should be able to catch a 16 megahertz input with a 100 megahertz sampling rate. But in this case, let's try and measure at least, see what we get. If we go from here to here, it says 60 nanoseconds, which is actually also correct, as our scope says, 60 nanoseconds. Though we have some fallouts here and there, and the duty cycle is not right, but that might be due to the missing impedance match. But look at that one, there's a big gap where we miss some readings. But otherwise, we have the reading, but we have some missing measurements. Let's try and raise up another step and go to 10 megahertz, which is then 100 nanoseconds. And let's try in Scana Studio and do another reading. Alright, here we go. Okay, that looks much better. It's fluent, no missing readings. Though the duty cycle is still a bit off, but that, yet again, might be due to the missing impedance match. Well, let's go to measure and see if it's true that it's 100 nanoseconds. Spot on. It is. So 10 megahertz is not a problem. One thing I'm missing here in Scanner Studio, though, is a little information window that displays me some information about the channel toggling. Like, let's say right now I would like to have the information that this signal is at 10 megahertz. On other software, logic analyzer softwares, you could be hovering above and be given and displayed the time, the high and low time for you. For example, the Sele, they do so as you can hover above the high period, the low period, and you can also get the whole period. In this case, with the Scanner Studio, I have to go into measure and do a measurement to get this 100 nanoseconds. So an information window with these times displayed for a current channel, or just the capability of enabling these information for a specific channel, would be a great feature. So now that we confirmed that the ScanaPLUS is capable of reading 10 megahertz signals without any obvious issues, let's go on and do some more comprehensive testing of the different decoder libraries. So let's connect it up to first off some a Uart device. I'll be using just an Arduino, and test some Uart transmitting, and afterwards we'll test some of the other features such as Can Bus and I2C. For the Uart testing, I've now connected this Arduino, the RX and TX pins, to the ScanaPLUS device, to channel 1 and 2. And I'll now, on the PC, program the device, but before doing so, I will start a capture, and this time it should be relatively long. So I'll set it to 5 seconds. And I'll probably set it to 10 seconds and start this capture, and then go in and program my device. Alright, done uploading. So the device should be running, and this program is a simple tick-tock program. So we go back to Scanner Studio and see if we can find any data. Oh yeah, we have some data there. And we can also see that this device is still here on the ScanaPLUS. It has an LED which blinks, indicating that there is a signal being changed on its inputs, which is because of the tick-tock serial example that I just programmed. But now on the PC in Scanner Studio, let's try and configure a Uart encoder by going to Decoder and adding a new one. Scrolling a bit down, we can select Uart. And in this case, we have RX and TX. We have to select which channel, because it doesn't really matter. Uart is Uart, so it will decode it as Uart with a specific baud rate, which is 9600. So we will do that for both. Yes. And I'll do it again for the second channel. Alright, so there we go. And now we should be able to zoom in. So I guess that is from Arduino to PC, and PC responds. And then the PC starts sending some packages. This is PC to Arduino. And when we get to here, this is Arduino to PZ. We have T, I, C, OD, and OA, which is line return. We'll probably change this to ASCII. No ASCII? No, there is no ASCII. There. T, I, C, character return, and line feed. And if we go a bit further, we can measure the distance between. It should be 1 second as programmed. One second, more or less. And we have TOC TikTok. Yes, that is correct. And we can, as before, go to the hex and get the hex output. If we scroll back down, see here at the end we have tick, tock, tick, and all the others is just the programming part of the Arduino being programmed, and the different colors indicate which channel it is. So Uart decoding is working, and working very nice. Is displayed alright. It can be a bit confusing to see these 1 and 0s when hovering above, but also they can be quite neat if you need to debug what is 35 in hexadecimal, what does it correspond to. So indeed Uart is working and is very intuitive to use. So when Uart has now been finished, I think we should go ahead and test some I2C instead. And for this I'll be using our Balduino mainboard, which has a MPU 6050 chip down here for sensor readings, the accelerometer and gyroscope, and we'll try to connect to that, the I2C line of that, and see what we can get. We are now hooked up the Balduino mainboard to the ScanaPLUS, the SDA and SCL lines, the I2C lines, which is already pulled up, has been hooked up to the channel 1 and 2 on the ScanaPLUS, together with ground, of course. So let's connect that for some power, and we'll notice that the LED on the ScanaPLUS starts blinking, indicating that data is being pulsed and sent into the device. So in the Scanner Studio, let's start a new workspace, discard the settings from before, and let's try and get a 100 millisecond sample and see if we can see anything. Alright, there, yes we do. Seems like channel 2 is SCL, let's confirm that. Channel 2 is the red probe, going to the white one, going into SCL, so that's correct. And back at the PC we have the data at the top, so let's try and add a decoder on this. Go to decoder, add an I2C, I2C decoder, have SCL at channel 2, automatically selected actually. Show SCL frequency, yes, let's try that. And data, yes please. Let's see what it says about that, if we can decode it. Not much in here, though if we go to hex we can see all the data. So apparently the data itself is not being displayed on the decoded data, even though it says format out here. But if we go to hex we can for sure get the data and see what it sends. Though I'm still missing an understanding and representation of who sends what. Oh, here we go. Sorry. We have the frequency. We have write. Oh, that's great. Here we go. Sorry. So that was just because it's the first package. We were missing some bits. So correct indeed. We have the write. It's writing to that one, that device, that register, reading from that device, which returns, and this register returns this. So yeah, indeed that works out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 data packages, and this is being pulled every. Can we snap on? Almost, maybe. Yeah. No, that won't work. Well, that didn't go that well. Try again. Alright, and no, that doesn't work. You can't scroll and add a measurement at the same time. But I can add this marker and then go to the end, and my marker disappeared. Well, software might be intuitive, but might also have a couple of flaws. Try one more time. You can see every 5.2 milliseconds, which is our polling interval at the Arduino. That's correct, because our PID loop is running at about 200 Hertz. So I2C seems to work, and you can decode the packages, though the hex output displays the compact, the packed data. If you go to packets, you will get this much nicer view of the especially transmissions as I2C, which is device and package specific. So we have address, write to something, this address, this data, and we read from the same device and it returns this data, and so on and so on and so on. I like this view. So except of small flaws and the missing marker specifics in the previous mentioned clock rates, I'm satisfied so far. So now let's go ahead and try some of the more advanced features of the ScanaPLUS, which is the built-in Can Logic converter. So you can connect up to a Can bus directly, which is RS485. So no need for an external RS485 Can bus converter chip, which is indeed handy, as you won't have to connect up any extra external circuitry. So let's try and connect up with the ScanaPLUS with a previous project of mine, which implements the Can bus system. Alright, I've now set up this test system, which is an STM32 board with a touch display, connected with a Can bus. This is the cable going to this smaller adapter board, which is a board with an STM8 processor that takes in the Can bus data and parses it out to some different digital and analog inputs, together with some interrupt management. This board is connected to the ScanaPLUS logic analyzer, the channel 7 and 8, which is one of the differential pair Can bus inputs of the ScanaPLUS device. So I've connected it to the Can high and low pin here on the board, together with ground, of course. So now we should be able to see and lock these Can bus signals. So let's go into Scanner Studio and take a look at the configuration in there. So now in Scanner Studio, we should first off configure the device inputs over here to support the differential pair inputs. So we select the Can bus differential lines, and it displays us how to connect Can low and Can high, which we've done. And now we are almost ready to start a sample. We've selected that we would like to have a 100 milliseconds sample window, so we press start, and some data has been collected. We can see the can lines, and now the final thing is just to add the Can Bus Decoder Library, or decoder, to the differential pair signal. So we go into here, the configure decoder, the CAN decoder, and select the channel 7 and 8, and select the clock frequency, which in this case has been detected to this number, but it's actually 100,000. Sorry, 1 million, 1 megahertz. So now we can finish this creation, this decoding, and we have decoded the data. And if we scroll in a bit, we can see that this data has an identifier of 0x100, which in this project case is the identifier where I'm sending data from the smaller board to the main board, the board with the LCD. Sorry. And then the rest of the data, we have 7 bytes of data, which is the following here, which is just the actual data package being sent from the board to the main board. In this case, the frame repeats. We have an end of frame here, and a new frame comes again, which is because the smaller board sends some interrupt packages all along to the main board. So there's not much window for other stuff here. But this is all true. That's the project, in this case, sending all these interrupt frames. So that's correct, and confirms that the CAN bus is working inside the ScanaPLUS, which is a neat feature as it's just connected directly to the differential pair lines and nothing else. So with the Uart and CAN bus and I2C confirmed, I think it's time to do a comparison with the Open Bench Logic Sniffer, which is also an FPGA based logic analyzer, but it's an open source logic analyzer based on a design by DangerousPrototypes. So I'm going to compare that, do some especially speed comparison and GUI comparison. So now let's compare the ScanaPLUS with an open source logic analyzer or logic sniffer board. This is the DangerousPrototypes Open Bench Logic Sniffer board. As you can see here, it's a bit larger board compared to the ScanaPLUS. It doesn't come in a plastic enclosure, it's just raw PCB. But feature-wise, it contains here 16 channels and furthermore 16 down here, so actually up to 32 channels. And if you go to the PC, you can see here that on the left we have the ScanaPLUS, 9 channels, 100 megahertz, 100 million samples per second, accuracy 10 nanoseconds. And if we go over here at the Open Bench Logic Sniffer, we'd see that the features are 200 megasamples per second up to 100 megahertz waveforms, and on 16 channels, that means if only the 16 channels on the right is used. Otherwise, it's 100 megasamples per second. 16 buffered channels on the right, those are 5 volt tolerant. And further on, it's an FPGA based logic analyzer, so it has some block RAM on board, and has some limited sampling depth though, whereof the ScanaPLUS seems to have unlimited sampling time, only limited by the PC. So that's at least a good feature of the ScanaPLUS, and for sure also the integrated receivers. So there's no need for external circuitry with the use of the ScanaPLUS. But now let's compare the two, both performance-wise, but especially also GUI. So the program, the Windows software wise, because the Open Bench Logic Analyzer's software is a lot different from the ScanaPLUS. So let's see on how intuitive they are, both of them. But now let's connect up this Open Bench Logic Analyzer board together with the ScanaPLUS to the same test environment as before, the FPGA board. Both logic analyzers have now been connected to the FPGA board that is now generating 50 MHz at the moment. And this 50 MHz signal is connected to the first channel on both logic analyzers, which is channel 0 at the Open Bench Logic Analyzer and channel 1 at the ScanaPLUS. At the PC, I've opened both applications. I've opened the Logic Sniffer, which is the Open Logic Sniffer project that is used to control the Open Bench Logic Sniffer logic analyzer. And in the background, I have the Scanner Studio as we just used. But let's start by trying out the Logic Sniffer application. Here in the capture dialog, you have to set up which port it's using, as the Open Bench Logic Analyzer is enumerating as a COM port USB 0 port. So I've selected the device, and I can go to acquisition, where I can select the sampling rate, the recording size, that's the sampling depth, which is set to maximum, and other different settings for channels and sampling. And then I also have a triggers dialog where I can set up some different triggers, and especially this down here, a value mask, so I can set up stage triggering for specific patterns on the input pins. Anyways, right now I'll just be sampling at 200 MHz, which is the maximum, and let's see which waveform we'll get. Alright, so that's the waveform, and this is the graphical user interface. If I zoom in, we still get some missing readings, but actually it seems like this is a fairly okay signal. We can see the toggling. Now if we go to diagram, we can go to different cursors when we place them, which can be done by right-clicking, set cursor 1, and a bit further, set cursor 2. And here we just move them a bit so we synchronize them right there. And we can go to Tools and say Measure to get the reading. And the reading says 50 MHz, which is correct. So for those places where we do have some signal, we can measure the 50 MHz, also as they proclaimed that it was able to measure up to 50 MHz signals. But GUI interaction wise, this software is not as good as the Scanner Studio. But if you do the same measurement here inside Scanner Studio, press start, we'll see that we just get the high signal as before. So now let's try and move the frequency down a bit. Just as before, we move it down to 16 MHz and do the same sampling, the same capture inside the Open Logic Sniffer application. And here we get a lot more samples and a fluent sample. If we use the same cursors to set about there, we can go into Tools and Measure and get that the frequency is 16.667 or distance 60 nanoseconds, which is also what the oscilloscope is telling us. So that is correct. Let's try and do the same inside Scanner Studio. See what it tells us. The same. Let's it's okay, except for some weird missing and longer periods. So it's not consistent as in the and with the Open Bench. But let's try and do a measurement on a proper one. Right there, 60 nanoseconds. So it's the same, it can do the measurement, but we still have some missing ones in here. Let's try and go back and then do one more step down in frequency. We'll have the 10 megahertz step. If we do the capture inside the Open Bench, everything is perfectly fine. Now the waveforms even start to look nice. And we move the cursor to do the measurement up there and up there. Tools, measure, 10 megahertz. Everything is fine. And in Scanner Studio, we do the same. Now they are looking fine, much better than before. If we move or make a new measure, it's also 100 nanoseconds. Alright, so that's about it for the performance testing. Now what about the different supported decoders and protocols? Well, in the Open Bench Logic Analyzer, these are what we have. We have one wire, I2C, JTAG, SPI, State, Uart. So some different ones, but in general, the GUI, the graphical user interface of this Logic Sniffer is a lot worse than the Scanner Studio. Though we have some higher sampling rates with the Open Bench Logic Sniffer, and we also have almost the double amount of full speed channel and even the quarter amount of channels if you are okay with 100 megasamples per second, which is actually the same as ScanaPLUS proclaims. And in terms of supported analyzers or decoders, it's almost the same, though the interface itself might be a little different. One thing I would like to mention about the Scanner Studio, though, is a really good and handy feature. That is the package and Hex Viewer, as you saw earlier. The package viewer is great for overview when you've logged and captured a lot of data and want to pack it together in the proper packets, especially for Can and I2C data, or even SPI data as well. And the Hex View is great because you can export these data to be used in, for example, let's say some C code where you need to redo a specific sequence that you probed around and analyzed with your analyzer. You need some processor to redo this sequence. You can copy that sequence from the hex code into your own C program. So in general, performing wise, I'm quite satisfied with the ScanaPLUS. I didn't expect it to perform as proclaimed, because a lot of logic analyzers is proclaimed to be performing better than they usually do when put to a real field test. As you noticed with the 50 megahertz waveform, it wasn't able to distinguish and see it. Though that makes sense if it's only 100 megasamples per second, whereof the Open Bench Logic Analyzer was 200 megasamples per second. Now if we go back to the Open Bench Logic Analyzer and try and set that capture rate to only 100 megahertz and then do the 50 megahertz input signal, we can see if that can capture anything at all. Actually it can, but we get something similar as before. So in general, a bit better performance on the Open Bench Logic Analyzer for the hardware itself, but for the graphical user interface the Scanner Studio is definitely better. Price versus performance, the ScanaPLUS is a bit to the expensive side, but indeed you get a nicely crafted product comparable to the Sale logic analyzer. So indeed the ScanaPLUS is a good fit for the engineer or hobbyist to use for very, very good and nice measurements, especially because it is a bit different with its 9 channels instead of only 8 channels, making it possible to do a full byte data sampling together with the clock or write bit. And together with that, the extra internal peripherals for connecting Can Bus RS-232, RS-485 and similar definitely makes it even better for the field engineer, as it comes enclosured with all these nice features. I hope you enjoyed this video review about the ScanaPLUS. Please feel free to leave any comments or questions and I'll try to answer them the best as I can. And if you'd like me to test anything else, please feel free to write us a mail. Thank you for watching.